In this lesson, we're going to talk about applied optimization problems. And this is a very common application in calculus. And the basic idea of optimization is that you have a particular variable that you're interested in, and you want to maximize it or minimize it. And a lot of times you'll have secondary conditions, and so you want to make sure that those conditions are met as well. Okay, so there's a problem-solving strategy here in this box where it talks you through what to do step by step. And we're going to follow this when we're working through our examples. So our first example says a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. And there's 100 feet of wire fencing. Determine the dimensions that would create a garden with a maximum area, and then we're going to find out what that maximum area is. So we need to find the dimensions that maximize the area, and then we also need to find the actual amount of area as well. The first step says to introduce all the variables, and if applicable, draw a figure and label all the variables. So I like to take the pictures that are in the book because it's a much better job than what I could ever do. So if you look at this picture here to the left, we already have that picture, and then the book defines the variable x as the sides that are running perpendicular to that rock wall, and then defines y as the length of the side that's parallel to the rock wall. For number one, I'm going to say see picture. So the variables are defined there and the picture's drawn. Okay, number two says determine which quantity is to be maximized or minimized and for what range of values of the other variables can be determined at this time. Reading the problem, what we're trying to maximize is the area of this garden. Let me write this down. We're going to maximize the area of the garden. Okay, and then let's see. Step 3 says write a formula for the quantity to be maximized or minimized in terms of the variable. This formula may involve more than one variable. So the area of this garden, since the garden is rectangular, is going to be length times width, so that's x times y. And so we have two variables here. In step 4, what we're going to do is we're going to rewrite the area equation so that it's all in one variable. So the other formula that we need to come up with is the perimeter for the fencing. We have 100 feet of fencing. We don't need it on the side with the rock wall. We only need it for the two sides that are perpendicular to the rock wall and then the one side that's parallel to the rock wall. So we're going to say that 100 feet of fencing is going to be equal to x plus x, so those two sides added together, 2x plus y. I want to use this information to write my area equation all in one variable. So my area equation is x times y, but I want everything in terms of x. So I'm going to substitute y as 100 minus 2x, and I get that from here when I solve for y. I subtract 2x from both sides, and then I can plug that in for y. So now I have my area function all in terms of x, and I can also write it like this. Now in step 5, it says identify the domain of consideration for the function in step 4 based on the physical problem at hand. Now this here is the graph of a quadratic, and it's an upside down quadratic because the leading coefficient is negative. Now, if I just gave this equation to you out of context, and I said, what's the domain for that equation? You should be able to tell me at this point that my domain is all real numbers, right? From minus infinity to positive infinity. But when we're talking about it in the context of a problem, we want to make sure that it makes sense with the problem. So if you imagine, here's my x-axis. I want to make sure that I'm using this part of the parabola here. I don't want negative area. And if I find out what that interval is, and I look at it on my calculator, or I solve it by factoring and setting it equal to 0, no matter how you do it, you're going to find that that's going to give you the interval from 0 to 50. All right, so we know we want to keep our domain for this particular problem, even though it's a quadratic, but for the physical problem of this garden, we want to keep it from 0 to 50. Okay, number 6, locate the maximum or minimum value of the function in step 4. This step typically involves looking for critical points and evaluating the function at endpoints. So we want to look for any absolute maxes or local maxes because we're trying to maximize. So we want to look for the highest point that we can possibly find. So we're going to look at the endpoints, and we're going to look at to see if there's any local mins or maxes and figure out which one is the highest. Now, if we did this problem in college algebra, which we have, something very similar to this, if not the same exact problem, we solve this problem by finding the vertex because we know that the vertex represents the highest point on that graph, and it's totally fine to do it that way. Now we're looking at it from a different perspective using calculus and derivatives. But whether you use the vertex or whether you use our calculus methods that we're learning now, you should still get the same answer. So I need to take the derivative of the area, and I'm going to get 100 minus 4x. Now my critical points for that, let's see, I'm only going to have one at 25, right? That's what makes the derivative of the area 0. Nothing would make that undefined, so I only have one critical point. So when I plug into the derivative a point to the left of 25, let's say 24 for my test point, I'm going to get a positive value. And when I pick something to the right of 25, let's say 26, and I plug in 26 into my derivative, I'm going to get a negative value. So this tells me that it's increasing on this interval and decreasing on the second interval. So if it's increasing and then it's decreasing, that's going to give me a local max, which is what we want. We're looking for local maxes. So potentially 25 could be our answer as of yet, but we also want to check the endpoints to make sure we're not missing anything. So if I plug in to the area function 0, I'm going to get, let's see, 0 times 100 minus 2 times 0, that gives me 0. If I plug in 50, that gives me 50 times 100 minus 2 times 50, that also gives me 0. If I plug 25 in, I'm going to get 25 times 100 minus 2 times 25. That's going to give me an area of 1,250 feet squared. This is definitely the better option of the ones that we've checked so far. We checked the endpoints, which gave us 0 area, and then we checked our local max, which gave us an area of 1,250 feet squared. So we're going to say that this happens, the maximum area happens when you have x is 25 feet. Now, if x is 25 feet, y would have to be 50 feet in order to have an area of 1,250. So these would be my dimensions for the garden. I would have the sides that are perpendicular to the rock wall is 25, and the side that is parallel to the rock wall would be 50 feet, and that would give us a maximum area of 1,250. Now, if you go old school on this and you check the vertex and you do it the way that we would do it in college algebra before we learned about the derivative, you would see that you would get a vertex. So you would have that your x coordinate is 25, And your y coordinate that represents the output or the area would be 1,250 feet squared. And then you can use that information to find the other dimension, which is the value of y, the side that's parallel to the rock wall. You would find that that was 50 feet. In the next example, we're going to maximize the volume of a box. And it says, an open top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. What size square should be cut out of each corner to get a box with the maximum volume? So you're looking to see, let me highlight it here with pink. You're looking to see what size square to cut out here in the corner so you can fold it up and create this box. All right, so step 1, we are going to define our variables. And so the sides of the square that we're cutting is going to be X according to the picture that I pulled out of the book. Then that's where the flaps can be folded up to form the box. And we're going to let V represent the volume of the box. And we'll do sides of square cutouts will be X. Okay, so step 2, the question is asking us to maximize the volume of the box. So let's write that down. We're going to maximize the volume. So we want to maximize V. For step 3, we want to figure out an equation for the volume of the box so that we can take the derivative and find the maximum. So the volume of a box is length times width times height. Step 4, we're going to use some kind of substitution with the given information to make everything in terms of our variable X. So the length of the box, once we cut out, let me erase this so you can see this again. When I start off with this piece of cardboard, if you notice, the whole length of the cardboard is 36 inches. But when I cut out a box in each corner, that's going to decrease that length by 2x. So when I fold up my corners, here is the length of my box. It's going to be this here because I'm cutting out these corners and folding it up. So my length is going to be 36 minus 2x. If I cut out those two x's, my width is going to be 24 minus 2x inches. So I'm going to plug that information in for my volume. So I'm substituting the length for 36 minus 2x. Then I'm substituting the width for 24 minus 2x. And then when we fold it up, the height of the box is going to be the length of x. So my height is going to be x. Now when I multiply all that out and I clean it up, I'll let you guys do that as some scratch work off to the side. But after you multiply all that out and you combine like terms, you should get 4x to the third minus 120x squared plus 864x. Now we need to think about the domain. This is a cubic function, and usually if I gave this to you out of context and I said, what's the domain of this cubic, you would tell me it's from minus infinity to positive infinity because it's a polynomial. But in the context of a problem, we want to make sure that we're picking a domain that makes sense for that physical problem. We definitely want to pick values of x that are positive. Also, when I cut my values of x, I want to make sure that I don't cut them so I have boxes that look like this, and then there'll be no bottom of the box. So we want to make sure that those x's are less than 12. So now for step 5, we're going to try to find any critical values. So I got to take the derivative. So I'm going to take the derivative of v, And I'm going to get 12x squared minus 240x plus 864. This doesn't factor nicely, so to solve this for critical values, you're going to have to use a quadratic formula. Since this is a quadratic, we can do that. You could also use complete the square. So that's another method you can use, but this definitely won't factor nicely. But no matter what method you use, quadratic formula or complete the square, what you should get for your critical values would be that x is 10 plus or minus 2 square roots of 7. Now, if I take 10 and add 2 square roots of 7, that's definitely outside the range of values we want to consider. So we're going to eliminate that as a possibility, and we're just going to keep x is equal to 10 minus 2 square roots of 7. And then when we put that in decimal form, just to get an idea of what that is, minus 2 square roots of 7, that's going to be approximately 4.708 if we round to 3 places. Just to give us an idea of what that looks like. Now, when we find our 4.708, when we put our critical value on our sign chart and we pick values to the right and to the left, I know I don't want to go too far to the right or to the left because remember, we want to stay on that interval between 0 and 12. So if I pick a test point, let's say I'm going to pick x is equal to 3. That's certainly in our range of values between 0 and 12. And then on this side here, I'll pick the test point 5. So these are our test points. Now, when I plug that into the derivative, I'm going to get, when I plug in x equals to 3, I'm going to get a positive value, which means this is increasing. And when I plug in x equals 5, I'm going to get a negative, which means this is decreasing. This is a local max. Now, if we check endpoints, if I plug into our volume 0 and 12, for 0, I'm going to get 0, right? Because I would plug in 0 here, here, and here. And that would give me 0. When I plug in 12, I'm also going to get 0. So this isn't going to maximize our volume at all. When I plug in, let's see, when I plug in 4.708 into the volume, I'm going to get approximately 1825. And since we're talking volume here, this is going to be inches cubed. We're plugging in inches here for the x. So when I cut out 4 squares, each out of the corners of that cardboard that have dimensions of 4.708 on each side of those squares, I'm going to get a maximum volume that is approximately 1,825 inches cubed. In this example, we're going to minimize travel time. The first 2 examples, we maximized something. Now we're going to try minimizing something. Now, it says an island is 2 miles due north of its closest point along a straight shoreline. A visitor is staying at a cabin on the shore that is 6 miles west of that point. The visitor is planning to go from the cabin to the island, and suppose that the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? All right, so the first step is going to be to identify the variables. So if you look at the picture we're going to use from the book is identifying x as the distance that the person runs, and y is the distance that the person swims. Oh, and we also have to mention t, since that's what we're going to eventually minimize. So t is the time it takes to get to the island. Okay, so these are our variables. Now, step 2, we need to come up with an equation that involves our variables here. So if you recall, distance is equal to rate times the time. The second step is to identify what you're minimizing. And in this question, it says we want to minimize the time it takes to reach the island. So that's what we want to minimize. We want to minimize t, our time. Step 3, we want to find an equation that involves these variables. We have the distance is equal to rate times time, and we can solve that for time by dividing both sides by r. So I have that time is equal to distance over the rate. Now, we're going to have 2 times here because we have the time that it takes for him to run and then the time that it takes for him to swim. And when we add that up, that's going to be the total time it takes for him to get to the island. So if I write down, let's use t, which is our total time. I'll write t total down here. The total time is the time it takes for the person to run, so I'll label that as TR, plus the time that it takes for the person to swim, and I'll label that TS. So the time it takes for the person to run is going to be the distance they ran over the rate that they ran. So since the distance is x that they're running, and the rate is that they run at 8 miles per hour, the time that they ran is going to be whatever the distance is divided by 8. Now for swimming, we identified the distance for swimming as y, and we know that they swim at a rate of 3 miles per hour, so we're going to divide by 3. So here's our equation for the total time it takes to get to the island. Okay, step 4. For step 4, we want to rewrite the equation that we have, so it's all in terms of x. So we need to substitute something else in there for y. So what I'm going to do is I have this triangle here. The entire length along the beach from the cabin to the island is 6 miles. So if this person runs x miles, then what's left over and that bottom leg of the triangle is going to be 6 minus x miles. So using Pythagorean theorem, we can come up with another equation and solve for y. So we would have that, in parentheses, 6 minus x squared plus 2 squared, which is 4, is going to be equal to y squared. And then so we'll get y is equal to plus or minus the square root of 6 minus x squared plus 4. But since we're talking about distance here, I'm not going to use the negative square root. I'm just going to keep the positive square root. So now I can substitute that in to our equation, and I'll have everything in terms of x. So my equation for the total time is going to be x over 8 plus, and now substitute in for y, 6 minus x squared plus 4 all over 3. So here's my equation where it's all in terms of x. Okay, so step 5, we need to identify the domain. Since the length along the beach, which is our x, which is what we have in terms of our function, since that length is at most 6 miles, I'm going to say that the domain is going to be between 0 and 6 miles. Okay, step 6. we need to find the critical values. So we're going to have to take the derivative of this function. So this is probably going to get a little messy. So off on some scratch paper somewhere, I'm going to have you guys find the derivative. Keep in mind that you can rewrite, because sometimes people don't see this, you can rewrite as x over 8 is 1/8 x. So when you take the derivative of 1/8 x, you just get 1/8. So off to the side, use your quotient rule and your chain rule and do all that to practice, and make sure that when you take the derivative of the total time, that you get 1/8 minus 6 minus x on top, and then on the bottom, 3 times the square root of 6 minus x squared plus 4. So there's your derivative. Now, to finish step 6, we need to find the critical values. So we're looking to see what makes the derivative undefined or 0. So let's start by setting this equal to 0. I could add that fraction that I enclosed in green from both sides, and then I can cross multiply. So when I add that fraction to both sides and I cross multiply, what I'm going to get is 3, then the square root of 6 minus x squared plus 4 is equal to 8 times 6 minus x. If I square both sides of the equation, I'll get 9 times 6 minus x squared plus 4. That will get rid of that square root. And on this side, I'll get 64, 6 minus x squared. Then I can distribute that 9. I have 9 times 6 minus x squared plus 36 is equal to 64, 6 minus x squared. I can subtract 6 minus x squared from both sides because these are like terms. And I'm going to get 36 is equal to 55, 6 minus x squared. I can divide both sides by 55. 6 minus x squared is equal to 36 over 55. Then I can square root both sides. We'll finish up here. And when I square root both sides and I add 6 to both sides, I get 6 plus or minus 6 over the square root of 55. And so these are my possibilities. Now, if I take 6 plus 6 over the square root of 55, that doesn't fall into our domain between 0 and 6. So I'm only going to use and look at x is equal to 6 minus 6 over the square root of 55. And if I put that in terms of a decimal, let's see what we get. 6 minus 6 divided by the square root of 55. That's going to be approximately 5.19. Remember, x is in miles. When we plug in 5.19 into our total time function, we get about 1.368 hours. If I plug in 0 into our total time, we get 2.108. Remember, we got to plug in our endpoints as well, and that's hours. And then if we plug in our other endpoint into the total time, if I plug in 6, I'm going to get 1.417 hours. Now, out of all that time, remember what we're trying to do. We're trying to minimize the time. So of all these times, we checked the endpoints and we checked approximately at 5.19 miles. This one has the smallest time. So we would say that she would run along the beach 5.19 miles and then start swimming, and that would mean that she would minimize her time and it would only take her about 1.365 hours. In the next example, we're going to maximize revenue. It says owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, where P is between $50 and $20, the number of cars N they rent per day can be modeled by the linear function N of P is equal to 1,000 minus 5P. If they charge $50 per day or less, they will rent all their cars. If they charge $200 per day or more, they will not rent any cars. Assuming the owners plan to charge customers somewhere between $50 and $200 a day to rent a car, how much should they charge to maximize their revenue? So step one, we have to define all of our variables, but it sounds like this question already did that in a lot of places, and we just kind of have to regroup and make sure we understand what they represent and write it down. So P is the price charged per day, and then we also have the revenue, and we'll call that R. Then we have, let's see, the number of cars. Step two, we need to identify what we're trying to minimize or maximize. And if we go back and look at the question, it says they want to maximize the revenue. Step three, we need to come up with a formula for these variables. Since we're trying to maximize revenue, I'm going to use that revenue is going to be the number of cars times the price. Step four, is we want to make sure everything is in terms of one variable. Since we additionally know a formula for N for the number of cars, the problem gave us that the number of cars is a formula itself, which is 1,000 minus 5P. So I can use that to substitute in for N and have everything in terms of P. So I have revenue is equal to, and then when I substitute that in for N, I get 1,000 minus 5P times P. And if I actually multiply that out also, I'll get 1,000 P minus 5P squared, which you can see this is going to be an upside down quadratic because my leading coefficient is negative. Okay, for step 5, we want to find the domain for our revenue function for the value of P. And they told us in the problem that they want to keep it between $50 and $200 for the price. So we're going to say that the domain is from 50 to 200. So for part 6, we want to take the derivative of R so we can find our critical values and look for any local maxes and look for absolute maxes. So the revenue we said was 1,000P minus 5P squared once we multiplied through. And so when I take the derivative of that, I'm going to get 1,000 minus 10P. So to find critical values, we're going to find the values that make this derivative 0 or undefined. Now, since the derivative itself is a polynomial, there's not going to be any places that the derivative is undefined. However, there is a place in which the derivative would be 0, and that would be at P is equal to 100. If I plug in P as 100, I'm going to get 1,000 minus 1,000, which is 0. Now, keep in mind that we want to stay between 50 and 200. So when I pick my test points, I want to make sure I pick test points on that interval. So I'm going to pick test point to the left of 100, I'll use 99. To the right of 100, I'll use 101. Now, when I plug in 99 into the derivative, I'm going to get a positive value, which means on that interval, we're increasing. And then when I plug in 101, I'm going to get a negative value, which means on this interval, it's decreasing. So that means if it's increasing and then decreasing at 100, that's a local max, which is what we were looking for because we're trying to maximize the revenue. So we would say that the price is 100 for that local max. And then if we plug 100 into the revenue of 50,000, that's a local maximum. Now we also want to check our endpoints to make sure there isn't anything higher if there's an absolute max. So we want to check 50, and we also want to check 200. If I plug in 50, then I'm going to get 37,500. If I plug in 200, I'm going to get 0. So this value right here, P is equal to 100, is going to be the best price to maximize the revenue. So if this company charges $100 a day for the car rental, they're going to get a revenue, or I should say a maximum revenue of $50,000. In this example, we are going to deal with a rectangle that is going to be inscribed in an ellipse. And the equation of the ellipse is given here. And then it says, what should the dimensions of the rectangle be in order to maximize its area? And then find the maximum area. So the first step is to identify and label the variables. So in the picture, we have the length of the rectangle labeled as L and the width of the rectangle labeled as W. If X is from here to here or from here to here, the length is going to be 2 times X. Same thing goes for the width. If I look at the width now, the width is going to be 2 times the value of Y. So let's write this down over here for number 1. The length is equal to 2x. The width is 2y. Let's see, and then we have the area of the rectangle. We'll call that A. In step 2, we have to list what we're trying to maximize. And in the question, it says we're trying to maximize the area of the rectangle. So I'm going to write down for step number 2, maximize the area of the rectangle. So step 3 is to come up with an equation for what it is that you're trying to maximize. So in step 3, our area is going to be length times width, which in terms of X and Y, it would be 2X times 2Y, which would be 4XY. In step 4, we need to find an equation for the area of the rectangle so that it's all in terms of X. Since the equation of the ellipse is x squared over 4 plus y squared is equal to 1, we can solve this for y and then do a substitution. When I solve this for y, I'm going to get plus or minus the square root, but I'm not going to use the minus because we're talking about distance here. So I'm just going to keep the positive square root. And then we're going to have 1 minus x squared over 4. Now, I can make that a little bit easier to deal with by getting rid of the fraction. I can make that 1 a 4 over 4. So I can combine those fractions. So I get 4 minus x squared, and then the 1/4 I can take the square root of and bring it out as 1/2. That'll make it a little bit easier to deal with without those fractions underneath the square root. Now that I know that y is equal to 1/2, the square root of 4 minus x squared, I can substitute that into our formula for 4xy. So I have 4x times y, which is 1/2 square root of 4 minus x squared. And then when I multiply the 4 times 1/2, we're left with 2x square root of 4 minus x squared. So this is our area of the rectangle, all in terms of x. Now for step 5, we need to find a domain for our area function, so the values of x that we want to look at. So notice that the ellipse goes out to 2 at the most. So our value of x, I would say let's consider between 0 and 2. Now in step 6, we're going to find the critical values and look for a local max and then check it against our endpoints to see if there's an absolute max. So we need to take the derivative of the area. So we're going to take the derivative of 2x times the square root of 4 minus x squared. This is going to need, you're going to need the product rule and the chain rule for this, because we have two functions. We have 2x, and then we have the square root of 4 minus x squared. And when you take the derivative of the square root of 4 minus x squared, that's when you're going to have to use the chain rule, because you have an inner function of 4 minus x squared with the outer function being the square root of x. So do that on some scratch paper off to the side, and you can check to see if you get the same answer that I do. When you take the derivative of the area, you should get 8 minus 4x squared all over the square root of 4 minus x squared. So now to look for the critical values, we're looking to see where the derivative is undefined and where the derivative is equal to 0. The derivative is going to be equal to 0 when the numerator is equal to 0. If 0 is equal to 8 minus 4x squared, so we're going to subtract 8 and then divide by negative 4. So we get that x squared is equal to 2. So x is going to be plus or minus the square root of 2. Now we're only considering x over the interval from 0 to 2. So we're not going to consider the critical point negative square root of 2. So we're only going to consider the square root of 2, positive square root of 2. Now let's look to see where the derivative could be undefined. To look to see where the derivative is undefined, you're looking to see what makes the denominator 0. And the only value of x that we could plug in that would make the derivative 0 on our interval from 0 to 2, if I plug in 2, that's when it's undefined. So on my sign chart, I'm going to put the square root of 2, and then I'm going to put the value 2. Now I'm not picking points after 2 because we're only considering the domain from 0 to 2. So I'm crossing off this interval. We're not going to use that interval. But I do want to pick test points here. So let's use x is 0 and let's use x is 1.9. If I pick that x is 0 and I plug that into my derivative, that's going to give me a positive value here, which means on the interval up to the square root of 2, I'm going to be increasing. When I plug 1.9 into the derivative, I get a negative value, which means on that interval it's going to be decreasing, which means if it's increasing and then decreasing at square root of 2, that's going to be a local max. But now we have to actually check the endpoints as well. So I want to find what the value is when x is 0, when I plug that into the area function, and then I want to check it when x 2. So when I plug into the area function that x is 0, we get 0. When I plug in 2, I also get 0. So this does not maximize my area at all. What maximizes my area of the rectangle is going to be when x is the square root of 2. Now to actually find the area of the rectangle when x is the square root of 2, I would plug that in. So I would have the area square root of 2. We will get 4. So the area is going to be 4, and then whatever the units are for the length, it would be 4 inches squared or 4 feet squared. It just depends on what the length, the units of the length are. So when x is the square root of 2, the maximum area would be 4. In the last example for this lesson, we're going to talk about minimizing surface area. So the example says that a rectangular box with a square base and it has an open top and a volume of 216 inches cubed is to be constructed, and we need to figure out what the dimensions of the box should be to minimize the surface area of the box. What is the minimum surface area? And a lot of times you'll hear companies wanting to minimize the surface area because when they do that, it minimizes the cost of the materials that they need. So this is a really good application for anybody in business that's manufacturing a product that comes in some kind of container. Okay, so for step 1, we need to find the variables and label them. So we have X that represents each side of the square base, and then we have Y is the height of the box. But then we also need to worry about the surface area. We'll call that S for surface area. Let's see, step 2, we need to indicate what it is that we're trying to minimize. And so we're trying to minimize the surface area, which is S. Okay, step 3, we need to come up with a formula for S. Now, one thing we need to keep in mind is the box has an open top, so there's nothing that's going to be on the top. So we're going to have 5 sides, not 6. So we have 4 sides and then the bottom. So the bottom has a square base. So that's going to be X squared. So this is the bottom of the box. And then we have to add the 4 sides. So each side is has an area of X times Y, and there's 4 sides, so we're going to have 4 times XY. Now, if there was a top to the box, then we would have to do 2x squared plus 4xy because we would have a top and a bottom. So that x squared just represents the bottom, and we don't need a top. Okay, step 4, we need to write this in terms of all X or all Y. Since we know that the volume of the box is 216 inches cubed, we can say that the volume is X squared times Y, and that's going to be 216, right? The volume of a box is length times width times height. So it's X times Y, and that's going to be 216. So what I can do here is solve this for Y, and then I can substitute it into our surface formula. So Y would be, if we divide both sides by X squared, I would have 216 over X squared. So I'm going to substitute that into our surface equation. I'm going to have S is equal to X squared plus 4X times 216 over X squared. And now we can simplify this, and X cancels on the top and the bottom. So, and then when I multiply 4 times 216, I get 864 over X. So here's the equation for the surface area, and all in terms of X. So in step 5, we want to consider a domain for this function. We definitely don't want X to be 0 because you want to make sure that there's some kind of length for that bottom of the box so that the box can actually exist. So we want X to be bigger than 0. But on the other hand, X can have any positive value, but the bigger X is, the smaller Y is going to be. So it's kind of like as X gets bigger, Y gets smaller because it's got to come up with that balance where the volume is 216. As long as we keep that balance, we can just say that the domain is going to be from 0 to infinity. There really isn't a way to put a limit on X. The previous examples, we were able to figure out an absolute max or an absolute min on a bounded interval. For this problem, it's a little bit more difficult. Okay, for step 6, we want to find the critical values. So we need to first take the derivative of our surface area. So when we take the derivative of the surface area, I'll let you do the scratch work, but check to make sure you get the same thing that I'm getting. We should get 2x minus 864 over X squared. So now looking to see where the derivative is equal to 0 or where it's undefined. Since we're saying that we're not going to let x equal 0 here because we need a bottom of the box, we don't have to worry about x is equal to 0 because we're not including that in our domain. But we can see what makes this derivative 0. Add 864 over x squared to both sides. And then we can multiply both sides by x squared to clear the fraction. So I would get 864 is equal to 2x to the third. I can divide both sides by 2. So I would have x to the third is equal to 432. And then I could take the cubed root of both sides, and I would get that x is approximately, let's see, the cubed root of 432. If we put that in decimal form and we round to 2 places, it would be approximately 7.56. Since we don't have endpoints to check here, because it's not a closed interval, we don't have 0 as an endpoint because we're not including 0. And infinity is not a point that we can plug in and check. So we're just going to check to make sure, since we're trying to minimize the surface area, we're going to just check to make sure that 7.56 is a local min. So I'm going to put this on my sign chart. I'm going to plug in test points. So let's say I plug in 7 for my interval to the left, and I'll plug in 8 for my interval on the right. Now, when I plug in 7 into the derivative, I'm going to get a negative value, which means it's decreasing on this interval. Now, when I plug in 8, I'm going to get a positive value, which means it's increasing. So if it's decreasing and then it's increasing, this is definitely a local min. So we can say that the square bottom of the box is going to have the dimensions of 7.56 inches by 7.56 inches. And then we can see what the y value is by plugging it into our formula up here, that the volume has got to be 216. So then if I take 216 and divide by 7.56 squared, I'm going to get that y is, if we round to 2 places, 3.78. And that will be the height of the box. So when the square base of the bottom of the box has dimensions 7.56 by 7.56, and when the height is 3.78, we can minimize the surface area and still keep a volume of 216 inches cubed.